So in the last video, we looked at vector spaces and subspaces and what it means for vectors to be linearly independent and for vectors to span a vector space. Now we're going to look at this idea of a basis. So what is a basis? A set of vectors is a basis for a vector space if the vectors span the space and are linearly independent. So the two main ideas within a basis is span and linear independence. So if a set of vectors both span the space and are also at the same time linearly independent, then we call that set of vectors a basis for the vector space. Let's look at some examples of a basis for R3, that is our three-dimensional space. So this set of three vectors, where each vector has three elements, since we're working with R3, these three vectors are both linearly independent, and they do span our whole entire space of R3, right? In other words, I can look at all linear combinations of these three vectors, and that would give me all vectors in R3. And also, I can't write one of these vectors in terms of the other two vectors. I can't write one vector as a linear combination of the other, so that means they're independent. Since they both are linearly independent and they span R3, these three vectors we call are a basis for R3. Another example of a basis for R3 are those three vectors, right? And I could say the same thing. These three vectors span R3, and I'd have to prove that, but just for now, just accept that they do span R3, and they're linearly independent, which I'd have to prove to you too. Another set of vectors that are a basis for R3 are those, and we do the same thing. We'd show that these three span R3, mean any vector in R3 I can write as a linear combination as those three vectors, and they're linearly independent. So those are three examples, and in a little bit we'll look at proving that a set of vectors is actually a basis for a vector space, but we're just going to ID here now. So examples that are not a basis for R3. Here's one example. A set of two vectors, 1, 2, 3, and 0, 4, 5. They are actually linearly independent, which we could prove, but they do not span R3. And if you think about it, if you look at all linear combinations of those two vectors, you'd get a plane in 3D space. Right? And the plane is not all of R3, so it does not span our space, R3. Well, what if we have four vectors? Well, it's possible with four vectors to span all of R3, but it happens that these four vectors are not linearly independent. And we could prove that. We'll wait. Just a little later, we'll prove things like this are not linearly independent, and so not a basis. But that's an example. That's not a basis for R3. And this set of three vectors is not a basis for R3. One way we could actually see this one immediately, if we look at the first two vectors and add them together, you'd get the third vector. That means they're dependent. You can write one vector as a linear combination of the other. So that's a dependent set. And we'd see if we looked at the span of those three vectors, we would get a plane in 3D space, even though we have three vectors. That's because the third vector lives in the plane of the first two. If you think of all linear combinations of the first two, the vector 1, 1, 1 would live in that plane. So the span of those three vectors is just a plane and not all 3D space. Now you might notice a pattern, at least for this example with R3, is that all those examples that are basis for R3 have three vectors. And when you think about, like if you just have two vectors and you look at all linear combinations, the most you can get is a plane. Well, that means you need a third vector, right? So you need three vectors to for that to span all of R3. But we also need them to be linearly independent. If the three vectors were not linearly independent, then that means you can't create all 3D space, because one would be a combination of the other, and you just have a plane at most. You could even just have a line which means all three vectors were just scalar multiples of each other, laying on the same line that passes the origin in those vectors. So you need three vectors to be a basis for R3, and you need them to be linearly independent. It's another way to think about a basis. We have this other idea, which should already be somewhat intuitive to you. It's the idea of a dimension. And now using the concepts that we already have, we can say the dimension of a vector space is the number of basis vectors representing the space. Right? So all these examples of a basis, there's three vectors that form the basis. That means the dimension is 3. So that's our definition of dimension. Right, and you already knew that, right? R3 is 3-dimensional. So that matches up with our intuition that the number of basis vectors is the dimension of the space. All right, let's check to see if a given set of vectors is actually a basis. And we'll look at R3 again. So is the set of 3 vectors a basis for R3? Well, so far we have 3 vectors, so far so good. We need 3 vectors to be a basis for R3. Right? If you had only 2 vectors, right, you can't get all of R3 just with 2 vectors, because at most that'd give you a plane. So we need 3. Now, the only question left to answer is, are these 3 vectors independent? And we've looked at how to find out if vectors are linearly independent or not. We check to see if, when we look at all combinations, linear combinations of the 3 vectors, and set it equal to the 0 vector, is there just only one way to make that linear combination be the 0 vector, or is there more than one way? If there's only one way to make that linear combination the 0 vector, that means the scalar multiples are all 0, right? Because 0 times the first vector plus 0 times the second vector plus 0 times the third vector is a 0 vector. And that means you can't write one of the vectors in terms of the other by rearranging the equation. But if there is some other way to linearly combine the vectors, so that's the 0 vector, that means I can write one of the vectors in terms of the others. One vector does depend on the combination of the other vectors. All right, so that means we set up the augmented matrix that represents the system of equations from scaling and adding up these vectors and setting it equal to 0. Right? So those vectors become the columns, and we augment the 0 vector at the end. Right? This represents the system of equations to see what those scalar multiples are, and we're hoping that the scalar multiples are all 0. So we can do a row operation, right? Replace row 3 with the sum of the row 2 and row 3 to get the more reduced matrix. It's not all in reduced echelon form, but we don't need to go all the way to reduced echelon form, because right away we can see from here that there is just one solution. There's not an infinite number of solutions. There's just one solution, and the one solution has to be the trivial solution. Which trivial, we mean the scalar multiples are all 0, right? The trivial meaning the easy solution, right? Because 0 times the first vector plus 0 times the second vector plus 0 times the third vector is definitely 0, right? That's the easy one. And the easy one is the only one, where the trivial answer, the trivial solution, is the only solution. So the only solution is when C1, C2, and C3 are equal to 0, right? Those scalar multiples are 0. So this is a basis for R3, right? They're linearly independent, and we know 3 linearly independent vectors will span all 3D space. All right, are these 3 vectors a basis for R3? Right? In other words, are they linearly independent, and do they span all of R3? Well, so the vector 1, 2, 3, 4, 5, 6, and 7, 8, 9 do the same exact thing. Those become the columns of our augmented matrix, and we augment the 0 vector on, because this would represent the system of equations that comes from looking at C1 times the first vector plus C2 times the second vector plus C3 times the third vector equaling the 0 vector. That represents that equation. So we're checking to see what solves this. We reduce the matrix, and we see in reduced echelon form the bottom row is all zeros, That means there's an infinite number of solutions, right? I can write C1 and C2 in terms of C3 in this case, like we've done before for writing a solution to an infinite number, describing the infinite number of solutions to a system. And that means I can write one vector in terms of the others. Right? So they're linearly dependent. There exists more than just a trivial solution. There's infinitely many solutions. So this is not a basis for R3. So some bases are easier to think about than others. And the easiest one is usually referred to as the standard basis. And for the purpose of our example, we'll think about R3 again. So this is set notation right here. What we mean by R3 is, in set notation, we like to use curly brackets, and we have like a little formula on the left. So it's the parentheses A, comma, B, comma, C. But what is A, B, and C? Well, that's the stuff that comes after the colon. So A, B, and C are any real numbers. So that's a way to describe R3, right? Some vector A, B, C, where A, B, and C are any real number. A, B, and C are arbitrary. So you can think about all like combinations, permutations of vectors with A, B, and C, where A, B, and C are any numbers that give you any vector in 3D space. You can think about all of those, the whole set, that is R3. So that's just kind of another way to write and describe R3. Now a standard basis for R3 would be these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is the easiest basis to think about. If we kind of check to see if this is a basis like we just did in the other examples, we'd check to see if they're linearly independent. Now just looking at it, we can definitely see that they're linearly independent. I can't write one of the vectors in terms of the as a combination of other vectors. But if you imagined writing the augmented matrix, you'd pretty much have the identity matrix on the left and augment the 0 column on the right. And we see right away it's already in reduced echelon form. So that's why we say it's the simplest. It's like immediately in reduced echelon form. And we see that the only scalar multiples that would solve that equation is C1 being 0, C2 being 0, and C3 being 0. So this is the easiest basis for R3. You can also think about for like our R3 space was described by the X, Y, and Z coordinate system. This would be unit vectors along each axis. So it's another way to think about it. Now, as I described in our video about vector spaces, our vector spaces does not have to be limited to just vectors containing numbers. Right, we've been mostly working with those because it's the easiest to talk about. Eventually, later in the course, we're going to move away from just vectors of numbers and think about vectors as functions instead of just kind of an ordered list of numbers. So, for example, a standard basis for what we call P2. What is P2? Well, what we mean by P2 is all polynomials of degree 2. So polynomial is P and 2 is degree 2. Another way to think about that is it's all parabolas instead of all parabolas or all quadratics, right, where A, B, and C are any real number. So x squared plus bx plus c, or A, B, and C are any real number. And you could check that that's actually a vector space. Remember, a vector space is just a set of objects that satisfies the 10 properties that we looked at before. You can double check that all 10 properties are satisfied. So this is an example of a vector space that's not just Rn, right? Like R3. The set of all parabolas is a vector space. And the standard basis, like the easiest basis to think about, the basis that represents this space, is vectors that are linearly independent and span all of P2 here. And the standard basis is 1, x squared. Right? So you can think of each one of those as a vector. 1 is a vector, x is a vector, x squared is a vector. Right? Vector, we're being more abstract now, it's just an object. But think about linear independence and span. Right? These are definitely linearly independent. You can't write one of the vectors or objects, or one of these functions, as a linear combination of the other ones. And also, think about scaling and adding up these functions. You can get any quadratic you'd like, any polynomial of degree 2, by just choosing the right scalar multiples. And the scalar multiples here we could call A, B, and C instead of C1, C2, C3, because we already see those scalar multiples in our general quadratic equation. So that's what we call a standard basis. It's just the simplest basis to think about for that vector space. All right, let's now look at a basis for a subspace. So this subspace W is defined as this vector with 4 elements. The first element is described as 4s minus 3t. The second element is s. The third element is t. And the fourth element is also s, where s and t are any real number. So you can think about all different ordered pairs of s and t and plug them into our vector with 4 elements. And that'd give you an infinite number of vectors. And we're thinking about that set of vectors where s and t can be anything, and all those different combinations of s and t. And we're thinking about a basis that would represent this space, right? We want vectors that are linearly independent and that would span this whole space, right? Well, what we could do is separate this vector into its s and t parts. What I mean by that is by splitting that vector into 2 and scaling one vector by s, one vector by t, and we just need to take those coefficients from the original vector. The coefficients in front of s are 4, 1, 0, and 1, and the coefficients in front of t are -3, 0, 1, and 0. Right, so we can split that vector into 2, and now it's written as a linear combination of those 2 vectors, right? So now think about all s and t, or any s and t, where s and t are real numbers. Right? That describes W. Think of that whole set of vectors. And we have those 2 vectors. Those 2 vectors are a basis for W. Right? You can double check. They're definitely linearly independent. You can't write one as a scalar multiple of the other. Right? Since you only have 2, you only have to worry about scalar multiple, not as a linear combination, since there's just 2 vectors and not more than 2. And it was definitely spanning W, because the way we just decompose the original vector into 2 parts, right? We can just recombine them to see that it gives us the original vectors, that original vector, the way it was described, by just scaling and adding up those vectors. Right? You do get back to 4s minus 3t, s, t, and s as each of those elements in the vector. All right, so those 2 vectors are a basis for that subspace. Those 2 vectors represent the subspace. A last little reflection on what a basis really is, well, imagine if you had just deleted one of the vectors in the basis. Well, if we only had that first vector 4, 1, 0, 1, then that doesn't give us our whole subspace, right? It would only give us part of it. So it wouldn't represent our whole space, because I need both vectors to scale and add up to give me my whole space. So that's what happens if you delete one of the vectors. You no longer span the whole space. If you added another vector onto that space, maybe like a linear combination of the 2 vectors, right? Well, then we already know it's dependent, but why does that matter? Why don't we want dependent vectors? Well, you just have some redundancy there, right? There's no need for an extra vector, because you only need 2 vectors to span this whole space. Right? You don't need a third vector. So it's like the most efficient. It's the minimum vectors you need, but you also can't delete any, because then you want to span the whole space. So a basis has both those aspects. You can't delete a vector because you want to span it anymore, and no need to add any more on, because that'd just be redundant. No need to add a linear combination of any of those vectors. All right, well, that's it for this video. Thank you.